Mr. Crispin here once again, and welcome to my workshop. Now today's video is a collection. A collection of what? I'll let you decide, but before you decide, let me introduce today's topics. First of all, I'm going to start with a little grinding theory. Second of all, I'm going to do some grinding, and thirdly, I'm going to show some upcoming grinding. So without further ado, let's make a start. So that was an example of some typical surface grinding, and basically there the wheel was feeding along, stepping over, feeding back, stepping over, feeding along, stepping over, and this continues until the wheel has totally cleared the workpiece, at which point the spindle height is lowered by the required depth of cut and the process repeats in reverse. This continues until the required height has been reached, and somewhere around the required height a few spark out passes may be taken where the wheel is allowed to continue moving back and forth over the surface without any additional cut depth being applied. This gives a period of grace for any strain in the machine setup to relax, and it gives you the ability to achieve the flattest possible surface for the setup you've got. Now the first point to make here is that as this is going on, the wheel is wearing. As the wheel is in contact with the metal, it's wearing, and although that's true of all cutting edges, it needs to be mentioned with regards to grinding, because in grinding the wear rate is significant. This is a standard aluminium oxide wheel, and in it there are approximately three things. There are aluminium oxide abrasive grains, which take the form of a sort of microscopic rock. There are pores, in other words air pockets, and there is the bond that's holding it all together. The bond in these typical traditional wheels is what we call a vitrified bond, and that is an almost glass-like substance, fairly hard and brittle, and it is holding all the grains in place with the air pockets all around. Now for a grinding wheel to wear, one of two things or both of two things typically happens. You have the abrasive grain held in the bond, and as it's cutting, the surfaces that it's cutting with become dull, therefore the force applied on the grain becomes higher the duller it gets. Now as this force builds, one thing that can happen is that the grain fractures. So the grain can't take it anymore, it fractures, and as it fractures the dimension changes and the wheel of course has slightly worn microscopically. The other thing that can happen is if the forces build up too much and the grain doesn't fracture and the forces overcome the strength of the bond, the whole abrasive particle itself comes out. So there are two ways in which the wheel has worn. Now some grains are actually designed to fracture. If you imagine this cutting as it's going dull, the forces are going up and the grinding is of a lesser quality, so if you can encourage the grain to fracture, when it does so, it reveals fresh cutting edges. In other words, it's sharp, and it is again sharp, and it can continue cutting. So some grains are designed to micro fracture, but those are the two typical forms of how a wheel actually wears. Now what are the results of that? Well, interestingly, even though this wheel is wearing, it can still produce a flat surface. And to explain this in more detail, let's have a little look at my first clipboard diagram of the day. Here I have depicted a wheel that has been dressed flat, so it's nice and flat along the periphery. Now as described earlier, as this is coming along, it's stepping over at each end, and let's say this is a 3mm step over, back 3mm step over. What you need to know is that if this is stepping over 3mm each time, although ultimately that full wheel width is going to end up over the component, only the front 3mm is going to be doing any work. If we feed over 3mm every time, it is only the front 3mm that actually gets any work. Equally, when going back the way, the back of the wheel gets all the work, so the back 3mm is actually doing all the cutting. Now, to show an exaggerated version of that, I have drawn this other picture. This is showing a greatly exaggerated wheel wear pattern, where basically the corners of the wheel that are doing the cutting have got the heaviest wear, and then there's a sort of sloping off period, because obviously as this wears, suddenly the next bit of wheel is exposed to more work, so it's a sort of continual wear. But the general pattern is that the wear comes down and the centre of the wheel is left in a much more usable state. Now, if your wheel actually looked like this, you would be redressing it with some urgency, but for the purpose of this explanation, let's imagine that this amount of wear is, say, 5 to 10 microns. So the corner's doing the work of worn 5 to 10 microns, but the middle is still in good shape. And so to answer the question I set out, how can a wearing wheel still produce a flat surface? Well, as long as the wheel is allowed to fully clear at both sides, it is the centre of the wheel that's responsible for the precision. So to clarify, in a scenario where the wheel can fully clear both sides, it is perfectly possible to produce a flat surface even when there is wear on the wheel. Let's imagine each corner is worn by 15 microns. It is still possible to produce a surface much flatter than 15 microns. Returning to my spindle nose, let's have a quick recap. This is the wheel I used for the job, aluminium oxide vitrified wheel, much like the surface grinder, and to produce this tapered portion, what I did is I dressed an angle on the wheel, and I then did a straightforward plunge grind to transfer the angle on the wheel onto this portion of the spindle nose. For working on the face, I dressed the face of the wheel to a relieved concave shape, what's termed as a dished wheel, and using that dished portion I then fed along the axis of the spindle such that the wheel fed directly into the face. Now, why did I choose to grind those features in that way? Well, to consider some alternatives, let's begin with considering how this might be turned. Here's my turning tool. To produce the taper, I'm going to feed along the angle, feeding along the angle, and to produce the face I would just use the cross slide and feed straight down the face. Now, to feed down this face and get a flat surface, I am assuming that from here to here the carbide tip has not worn. Now, that's a pretty safe assumption. Okay, there might be some microscopic wear that I can't detect, but it's a safe assumption that from here to here the cutting tip has not worn significantly. So let's now return to the grinding wheel, and with everything I've discussed so far in mind, let's have a look at the potential caveats of other approaches. So imagine, for instance, I thought, I know, I'm going to treat this a bit like a turning operation. I'm going to just put the wheel here and I'm going to feed along, and I'll let this corner do the work. Maybe that would be a good idea because it's going to reduce the spindle load. There's a lot more wheel in contact doing this than there is with a corner, so less spindle load, therefore is it a better option? Well, the problem is that between here and here the wheel wear is going to be significant enough that you will not produce a straight face, you will produce a slope. As the wheel feeds across, it is wearing, and therefore as you go along you get more and more metal on, giving you a slope as you go across, so you don't produce a flat surface. The same would be true even if I stuck with the current setup and I had this dished wheel, but I started here and fed along the face. This dished wheel is highly prone to wheel wear. In fact, it's wearing as soon as you touch on, and the reason it works as a plunge grind is because the face is wearing evenly and it's spinning, and as it's wearing back it is still maintaining the same geometry with, you know, the relationship of this face to the spindle. It is wearing back in an even fashion and the geometry is remaining the same. If I was to try and start here and feed across the workpiece, then as it wears backwards, the surface becomes a slope. So be very careful in treating the grinding operation like the turning operation. Because of the difference in wear rate, you get a dramatically different outcome. Perfectly good with the turning tool, that's going to give you a straight face, but a grinding wheel is not going to give you a straight face treated in either of those fashions. There is a halfway house that could be carried out. If you didn't have the spindle torque for a full engagement, you could sort of nibble it, so you plunge grind in, then step over and plunge grind in again until the surfaces blend, and you keep plunge grinding in and in and in until you've covered the whole area. That way at least you are producing an overall flat, but it is more fiddly. There's an example of that shown by Don Bailey in one of his grinding videos, Suburban Tool Company. Moving on to the grinding of the taper, there are options here as well. Now, first of all, while we're on the topic of corner wheel wear, could I treat this as a turning tool again and feed along? Well, I could, but the same thing is going to happen. The corner's going to wear and I'm not going to get a great taper. There is, however, an alternative approach. Because this time I'm working on the periphery of the wheel, what I could do is I could start here and feed along the angle, and this will be a bit easier for me to show you with the clipboard. Imagine here's my wheel, here's the surface of the taper I'm grinding. I could actually feed the wheel along the angle so that that portion of the wheel is working all the way along at the same angle. Now this gives an effect a bit like the surface grinder. The front corner is obviously going to be doing the work, but you've got the rest of this surface that's there to do the precision. So as it comes along, yes, the front corner will wear, but you've got all that remaining wheel to do the cleanup and precision part. Why could that still be a problem? Because it worked on the surface grinder. Well, the big difference between this and the surface grinder is that I don't have the ability to feed all the way beyond. I'm coming up to a shoulder and I can't go all the way beyond like I could on the surface grinder. If you're in a position where this wheel could feed all the way past and all the way back, then that same wear pattern I showed on the surface grinder would apply and you would probably get a good job. Now imagine that the wheel wear on the corner was that small that it actually fitted into that relief groove. Perhaps you get away with it, but I would be concerned as I fed along that the front of the wheel was wearing and I would not be able to lose that wear in the cutout groove. So these are the things to consider when approaching a grinding operation. Now you will be relieved to know that I only have one topic left in this grinding theory talk, and I'm going to try and demonstrate it with a bit of live drawing. This topic is around one of the downsides of doing a plunge grind on the periphery, and that is in terms of surface finish. Imagine as this wheel is spinning that it has lots of little imperfections all down the length of the surface. So as this is spinning, it is actually going to describe a, hang on, where's my pen, just a moment. Right, I found the pen, it was in the drawer with my brother's toothbrush. So here is the grinding wheel spinning, and although you might consider that that edge is actually a nice smooth line, because of the dressing method, the coarseness of the grit and other imperfections, actually what is there in microscopic form is a rough surface. And bear in mind that this isn't, I'm not talking about a cross section of the wheel, because this is spinning. So this is the overall form described by the spinning periphery. It's not perfectly smooth, it has jagged edges to it. So as this plunges in, it is not plunging onto the surface a perfectly smooth edge, it is actually plunging on a surface with whatever jaggedness it has in. Now, a bit like I mentioned earlier with the dulling of the cutting edges, these sharp points fairly rapidly break down in standard grits, so some improvement is gained just through the cutting of the metal because these break down, but you are still left with imperfections such as that. And the downside of the plunge grind is you go in, you come out, whatever is on the wheel is directly transferred to the surface, minus the dulling effect. So one potential solution is to combine the plunge grind with that method I talked about earlier of doing a slide along the angle. So for instance, I could plunge in and then do a side shimmy on the angle by maybe 1 millimeter and then back again. So in practice, if on the paper is my wheel, I plunge onto the taper and then on the same angle as the taper do a side shimmy, and what that does is it allows the extreme points of all those little raised portions to level out. Right, well, following that, the best thing to do is probably to pretend it all made sense, because then you won't have to hear me go through it again. With that said and done, I will now return to the lathe and carry out a little investigation. So I ground a tapered portion and I ground a flat surface. Well, how flat is this surface? To have a little look, I have taken a slip gauge, which I class as being very flat, and I've put a thin layer of blue on it. And I'm now going to do this. And examine the flatness. Now, if this wasn't flat, I would see blue at the sides and not in the middle. But as you can see, there's blue all the way across, and now there's even less blue on here. Let's try again. So it is generally very flat. But why am I doing this? Well, if the surface was exactly right, what I would actually see on here is a crisscross where both sides of the wheel, wherever it's gone here, both sides of the wheel have been lying on the same plane and have left a crisscross, or what is sometimes known in grinding as a laced finish. But as you can see, I've got the curves going one way but not the other way. So that tells me that, seeing as I was grinding here, the spindle is slightly tipped like that, because this portion is leaving the finish, this portion is not. So whilst I've got the camera here and I'm feeling experimental, I'm going to set my dial indicator up again and have a look at the spindle orientation in relation to this surface and see if the spindle is indeed looking slightly downhill. You are now positioned at the back of the lathe looking over the top, and what you can see here is a dial indicator mounted to the grinding spindle. Now, when using an indicator in this horizontal fashion, it's worth bearing in mind the effects of indicator droop and bar sag, as those factors are working on the measurement assembly, and I have a video on this titled "Are You Suffering from Bar Sag?" Basically, to minimise the effects of bar sag, I'm using all steel pieces, no hydraulic holders. I have kept everything as short as possible, it's as far in as possible, and it's all done up tightly. Now what I'm going to be doing is comparing the angle or axis of this spindle in relation to the face I've ground, and you'll see that shortly. First of all, I'm going to set the clock to 0, and down at the bottom here I'm required to use a mirror, and when using a mirror I like to pick the mirror side as the 0, because that way you can't get mixed up between is the clock going plus or minus. So let's make the mirror side 0, and I am now going to bring the indicator back up to the top. It is currently reading plus 2 thou, which means that there is more of a loading on at the top than there was at the bottom, which indeed means the spindle is looking slightly downhill. If you were to consider the middle 0, then it's a thou error over the radius, top to bottom 2 thou. Now when I set this up, first of all I was doing it off a 4-inch diameter. This is significantly larger. I think I got the 4-inch diameter to within a thou. Done quite a bit of grinding since then, so perhaps there's small variations, and obviously a larger diameter is going to show a larger error. So what I'm going to do is now correct this, get 0 and 0, and then try again and see if I can get a proper laced finish. For interest, I'll just bring this back to the 90-degree position. That is good. Obviously I'm 0 to 2 thou, and I'm reading 1 thou in the middle, so that tells me that you know, I'm pretty much dead on with regards to the angle that way. It's just a looking down error, and I can take this all the way around the back if I can get over that little step without disturbing anything. And yeah, so it's reading plus half a thou, plus half a thou, plus 1 thou. So this way on is within half a thou over that length, but up and down I'm going to try and improve. I have now got that within half a thou, and for reference that's on roughly a 170mm diameter, which happens to be 5 times bigger than the diameter of this wheel. So half a thou, 5/10 over that diameter is going to be 1/10 worth of error over the size of my wheel. So if that doesn't give me a laced finish, then I'll eat my shoe. A crisscross has been achieved, so with that I will move on. So somebody is going to want to know, how did I adjust the presentation angle of the spindle? Did I put packing in somewhere? Did I regrind something? Well no, all I actually did was I adjusted the position of this disc. Now what you need to know is that this disc is not parallel. During the initial setup I had to grind a shallow angle across it, so it is actually thicker at one end than the other by about 0.2 of a millimetre. So how does adjusting the position of a disc that is not parallel have any effect on the spindle's presentation angle? Here I have a piece of metal with an angle in it, much in the same way that I have a disc over there that has an angle in it. And what I said was that by rotating the disc I was able to affect the spindle presentation angle. Well, how is that possible? Let's do a little demonstration. Imagine that this is the disc, and imagine that this is the grinding spindle. Now I'm going to keep this pointing in a certain direction, straight down, and as I rotate this angle, watch the relationship between the top edge here and the drawers. Once more. You can see that the angle as viewed from the direction you're looking at is influenced by the rotation of the angle. Now what's actually happening here is it's all about the angle as viewed from a certain plane. So when considering this plane, the angle is changing. What's actually happening is here the square is pointing down, but it's vertical this way, and when I rotate the angle round, suddenly it's square this way, but now it's out of kilter this way. So that is the effect I was exploiting by rotating the disc. Observant viewers will remember that when I set this up I filed a nick in the disc and I set the nick here. So as you can see I have rotated the disc round from its original setup. So the spindle nose is now done with a capital D, but what about the things that fit onto it? You are now looking at Mr. Crispin's next job. Some of you will remember that the reason I reground the lathe spindle nose is because it had sustained heavy damage on the taper where pieces of swarf had been stuck between mating surfaces. Now these three pieces of tooling are ones that came with the lathe, and as you might expect, the internal tapers of these are equally damaged. So while I've got the grinder set up, I want to regrind these inners, and to do so is going to involve a bit of chess, because I don't want to put these pieces of tooling on the lathe until I've reground them, but equally somehow I've got to hold them on the lathe to regrind them. So this is going to be the unlocking article. I'm going to start with this on the spindle, and then one by one come up with a way to hold one of them on here. Then once I've held one of them, I can use a bigger piece to hold the next piece, etc. So I haven't decided exactly how I'm going to do that, but the willing man will find a way. And then to conclude this lathe spindle topic, I will be taking this new back plate and mounting to it an ER40 collet chuck. Some may remember the ER40 collet chuck I made for the Myford. So I'm going to have a equal setup on the Harrison so that I can use the same collets between the two machines. Well, that's it for this video, and that's it for the year 2022. I have enjoyed producing the films that I've made this year, and I'm looking forward to next year, where I will be beginning with the lathe tooling work, and I will then be moving on to the spindle valve guides for the locomotive cylinder blocks. Now, thank you to those of you who have supported this channel through the purchase of some Mr. Crispin merchandise. And just to answer the question around international shipping, yes, these products can be shipped anywhere worldwide. However, it's worth bearing in mind that actually a lot of the printing departments are spread out across the world. So say in America, if you order something, it doesn't get printed here and shipped to America, it just gets printed in America and shipped internally. Aside from that, my condiments of the season to all of you. Thank you for watching. I hope you found this interesting, and see you on the next video.